Welcome to the second video in an 8-video series on rational expressions, reducing. So before we start the actual reducing rational expressions problems, there's a few concepts that we need to clarify. First, let's start with this obvious division problem. We all agree that 10 divided by 5 is 2. And our notion of division is that it's the opposite of multiplication. 10 divided by 5 equals 2 is true because 5 times 2 gives a result of 10. And this conforms with our general notion of what division should mean. But let's talk about division by 0. I'm going to make 3 proposals of division problems involving 0. Only one of them is going to prove to be true. Proposal 1. 0 divided by a non-zero is 0. I just randomly picked the number 6 here. Proposal 2. A non-zero divided by 0 is 0. And proposal 3, 0 divided by 0 is 0. Now on first glance, one would think that any division problem involving 0 has an answer of 0. That turns out not to be true. Let's go through the reasoning. Let's look at proposal 1. Does it conform with our notion of what division should be as the opposite of multiplication? Well, if it does, then 6 times 0 should give this result, which it does. So far, so good. Let's analyze proposal 2. This times this equals this. That's not logical. So it's not a good mathematical choice to claim that dividing by 0 gives an answer of 0. How about proposal 3? This times this equals this. Well, that does also conform with our general idea that division is the opposite of multiplication. But wait, what if I were to make a ridiculous claim, like 0 divided by 0 is 3? That would also fit the pattern, this times this equals that. And that's not very logical. And if that were our only criteria for division by 0, then there would be infinitely many answers to the question 0 divided by 0. So proposal 3 isn't very logical either. Now looking back at proposal 1, it turns out mathematicians have decided, and for good reason, that the only time a division problem would equal 0 is if the top is 0 and the bottom isn't. As far as the other two cases, either time your denominator is 0, we say that that fraction does not exist. And it's commonly said that division by 0 is not allowed, or the denominator can't be 0, or such things. Let's move on to another idea unrelated to 0. This is a fact that you've known probably since elementary school. Anything divided by itself is 1. 5 divided by 5 is 1. 17 divided by 17 is 1. If anything divided by itself is 1, how would that work in algebra? Would this thing divided by itself also equal 1? Question mark. Well, let's explore that a little further. What if x were 100? I'm not suggesting that this is a math problem you're going to be doing. I'm just running you through some ideas. If x were 100, that fraction would indeed work out to 1. Random number, what if x were 37? I'm just leading you through some thoughts here. If x were some random number like 37, this fraction would also equal 1. And it seems like this fraction would always equal 1, but what about x being 2? If x were 2, this fraction doesn't exist because x being 2 would cause the denominator in particular to be 0. So back to the question, does this expression equal 1? Well, usually it does. If x is any number other than 2, this expression does equal 1. So in mathematics, we loosely say that this expression is 1. What we really mean is it's 1 almost everywhere, with the minor exception of x being 2, which we often don't mention at all and simply claim that it equals 1. Alright, there's our second idea. Anything divided by itself is 1. Let's develop another idea about fractions that is going to eventually help us get through the problems in this video. Suppose we were multiplying fractions. Here's an example. You may recall from elementary school or middle school that when you multiply fractions, you multiply straight across the tops and straight across the bottoms. Now on a calculator, 21 divided by 10 is 2.1, but in algebra, we tend not to use decimals and we like to keep everything in fraction form, so I'm going to keep this as 21 over 10. Now, while we tend to look at this as a math problem on the left and an answer on the right, there's a more broad way to think about this. Think about these as two numbers that are equal to each other. 3/5 times 7/2 is a number, 21/10 is a number, and both of those numbers are the same. Now, while we're conditioned as math students to think of this as problem and answer, is there any time that we would want to take a fraction, go the other way, and split it up into a product? Well, that seems counterintuitive, but it turns out there's some interesting moments where that's actually beneficial. Now, it wouldn't do us any good here in this example, but let's take this example and see how splitting up one fraction into a product of two can actually be helpful. Now, on a calculator, which we're not really using in algebra, 51 divided by 68 would give us a decimal. Good enough. That's not our focus here. Let's look at a way that we can do this division problem or reduce this fraction without calculators or decimals, which is sort of the algebra tradition. Suppose I were to tell you that 51 is 17 times 3 and 68 is 4 times 17. Now, these aren't facts that most people have memorized, but they are true. And what if I were then to take that and split it up as a product of fractions to answer the earlier question, is there ever a time when we would split a fraction up into two? Well, in this case, it doesn't seem to have done much good, because I've split 51/68 into the product of two fractions, neither of which is simplifiable. Everything I've done here is valid, but I think it's also pretty useless to split it up that way. What would happen, though, if instead of splitting it up that way, I split it up this way? Also valid. Now that's valid and useful. Here's why. By splitting it up that way, 17 divided by 17 is 1. Anything divided by itself is 1. And here's another rule from elementary school. 1 times anything is itself. And so you can see that by splitting up a fraction into a product of fractions, one of those fractions had a value of 1, which greatly simplified the result. Now, before we move on, many math teachers would simply tell you to cancel the 17s and say, oh, the answer is obviously 3/4. And while they wouldn't be wrong, I don't think that's a good idea for a student to do necessarily right off the bat, because the minute you start canceling things from the top and bottom of a fraction just because they're the same, most students will overgeneralize that and start crossing out any two identical things that appear on the top and bottom of a fraction, which isn't always possible to do. So I recommend that you work it out the long way by splitting it up into a product of fractions. More on that later. Now, if you watched video 1, the claim was made that this expression reduces to x over 2. Now I'm going to give you the details of that claim. So, here's our first actual problem that looks like something you'd see in an algebra course. Suppose we want to reduce the fraction on the left. The main trick you want to do when reducing fractions is factor. Now, I've produced a 7-video series on factoring, and it's quite extensive. To understand the rest of this video, we will be relying heavily on videos 2, 4, and 6 of that series. if you're going to watch the rest of this video, you either have to be decent at factoring, watch those videos, or be willing to just sort of suspend that thought as something you're going to learn later. But I won't give any explanations of the factoring here because it will greatly diminish the pace of this video. Alright, with that advisory, let's move on. The first thing I'm going to do to this problem is factor the top and bottom. Now, one thing you'll see throughout this video is the pause symbol. When the pause symbol shows up, it's a reminder that you might benefit by pausing and checking the factorization yourself. Again, I won't explain any of the factoring in this video, so I'll leave that to your own devices. The point of this video is to show you what happens after factoring. After having factored this, I can split this up. Now, most math teachers would say, oh, the x minus 3's cancel. And while they wouldn't be wrong, I'm going to recommend that we not use that logic. Again, because students who start canceling things out of fractions generally go beyond what they're allowed to cancel, and it's not an advisable strategy in my opinion. There are times to do it, times to not do it, and the complication of when to do it and not do it isn't worth the trouble. But you can see when to do it because, in this case, because everything is factored, we can split this up into two fractions. Now, look at the x minus 3 over x minus 3. Using the fact that anything divided by itself is 1, and the additional fact that anything times 1 is itself, I've now reduced this all the way to 4x over 8. But you can see this isn't x over 2 as we claimed it was. That's because the fraction reduces further. See the 8 in the denominator? I can factor 8 into 4 times 2. Now, because this is everything is factored, I can split the factors into two fractions, use the fact that 4 divided by 4 is 1, and the fact that 1 times anything is itself, showing that the answer is in fact x minus 2, as we saw briefly in a prior video, without proof. Here's another problem. Now, in order to reduce this, we have to factor first so that we can split it up into two fractions and hope that one of those fractions has a value of 1. Here's the factorization. And I can now split that into a product of two fractions. Notice I've pulled the x minus 3's together, again to use the fact that anything divided by itself is 1, and the fact that anything times 1 is itself. And now I have the simplified version of the original fraction. Side note, something not to do I've seen students do quite often. Students will take a fraction like this, split it into 2, cancel the x's, and either get this or simply 2/5 as if the x's were to vanish. None of that is allowed because you can't split a fraction into a sum of fractions by just breaking it apart that way. This only works when the top and bottom are factored and when you split the fraction into a product. That is allowed. Nothing that you see on the right side of your screen here is allowed. So now, there is the so-called answer to this, but let's go beyond the answer. Question: would these two expressions always be equal? In other words, if I picked some random number for x and plugged it into both of these, would I get the same result for both? Almost everywhere, yes, that would be true. There is one exception. These two things would not equal each other when x is 3. Do you remember earlier in this problem when we asserted that x minus 3 divided by x minus 3 was 1? But that's normally true, but not when x is 3. It's true at any other time. So while we generally tend to say that these are equal, it turns out they're not equal when x is 3. Now that doesn't stop us from saying that the fraction on the left reduces to the fraction on the right, but we have to have this understanding that it's true for almost every real number. just not 3. Watch what happens when x is 3. If I were to put 3's literally into every x, now I did some scratch work I didn't show here, but scratch paper shows this. 0 divided by 0 and 5/8 are definitely not the same. One of them doesn't even exist. Now, I'm not suggesting that when you're done with a math problem, you should necessarily analyze what x can't be for these to be equal, but it's worth thinking about once in a while. But generally speaking, we simply call the thing on the right, quote, the answer, without mentioning that the two expressions aren't equal when x is 3. Here's another problem. So in order to reduce a fraction, I have to factor. And now that I've factored, I'm going to do an unusual thing with powers of x. Watch this. Notice I've changed x to the 5th into x cubed times x squared. Why on earth would I do that? Well, by choosing to do that, I have arranged for a factor in the numerator and denominator to be the same. And by arranging that, I can factor those out as a separate fraction. Use the fact that x cubed divided by x cubed, or anything divided by itself, is 1, and then the fact that 1 times anything is itself to simplify this fraction. Now that may seem a little strange, and most math teachers, many math teachers, might just say, oh, there's a rule for powers of a factor, simply subtract the exponents. Notice that 5 minus 3 is 2. Now there's nothing wrong with that shortcut, but with every shortcut comes a danger of overusing it. I've noticed that students who simply subtract the exponents as a shortcut will get problems like this right without going the long way as you saw me do, but those same students typically will overgeneralize and start subtracting exponents all the time, even when they're not supposed to. So I don't recommend the shortcut of subtracting exponents unless you know when to use it, but it's more complicated than you would think. So better that you work it out the way you saw me do it. So here is the reduced version of this thing. And as a sort of afterthought, notice that the numerator has a product of factors in it. Question: should I distribute that x squared to the parentheses, giving me an unfactored version as my answer? Well, there's no general consensus among mathematicians as to which of these two things, either the center or the right of your screen, is a better version of the answer. They're both reduced and they're both simplified as much as you can. And most math teachers would be willing to accept either one of those as a final reduction. Again, there's no mathematical consensus on which one of those is better. It's more of a matter of opinion than fact. Here's another problem. All right, to reduce, I'm going to factor. Then I'm going to pull out the common factors. Notice the x minus 5 is sort of in its own fraction. To make this a proper statement, we should put a 1 here. Then, using the fact that anything divided by itself is 1, and anything times 1 is itself, gives us this as the result. But wait, anything divided by 1 is itself. So while x plus 5 over 1 is technically a reduction of the original problem, x plus 5 itself, the non-fraction answer, is even better. And most math teachers would expect you to go that last step. Now this problem that we just finished, I want to look at the same problem flipped over and watch what happens in this case. Okay, step 1, factor. Step 2, pull out the common factors into their own fraction. We'll put a 1 here to be proper. Anything divided by itself is 1. 1 times anything is itself. And here's a common mistake. Don't do this. Many students will ignore the 1. But there's no rule that 1 divided by a number is itself. In other words, when the 1's in the numerator, you've got to keep it there. It would make no sense to eliminate it. Now, before we can get back to the business of looking at our final example, I need to sort of stop here and develop another idea. The idea of reversed subtractions. I'll tell you what I mean. Here's 2 subtraction problems that are reversed in the sense that the numbers are in the opposite order. Obviously, 12 minus 7 is 5, and 7 minus 12 is negative 5. So when we talk about reverse subtractions, that's what we mean. What happens when you divide reversed subtractions? Well, if we were to work this problem out, we would get 5 divided by negative 5, which works out to be negative 1. Let's look at another example. What happens when we divide reversed subtractions? Well, in this case, we also get negative 1. Well, that poses a more general question. What if we have reverse subtractions in an algebraic sense? Would this also equal negative 1? Well, it turns out it generally does. Let me show you the details. Now, before you see this, I have to warn you, it's a little confusing, and it's not as important that you get the reasoning behind it as you just know that that fraction reduces to negative 1. So ultimately, you can simply be happy to say, okay, that reduces to negative 1, and I'm good enough with that. But I do feel obligated to show you the rationale. What if I were to factor a negative 1 out of the denominator? Notice the change here. Now that seems like a very strange thing to do. Why would I want to factor a negative 1 out of the denominator and make the whole thing uglier? Because by doing so, I'm able to simplify this way. Notice these 2 things in the box are algebraically the same. And by having factored a negative 1 out of the bottom, I can then split it into 2 fractions and use my same logic. Anything divided by itself is 1, and that proves that that equals negative 1. If that logic escapes you, as it does most people, suffice it to say, the important thing here is the result that we're going to use in the next problem. When you divide reversed subtractions, we call this the division of opposites technically, you get negative 1. Here's a problem where we're going to use this idea. Let's use the idea that dividing by reverse subtractions is negative 1 in this problem. First we factor, then we split that fraction into the product of 2 fractions. Now notice I've put the x minus 5 and the 5 minus x, the reversed subtractions or the opposites, in the same fraction. Because by doing that, I can say that that fraction on the right equals negative 1. That's my simplification. Okay, that brings up another question. How do we multiply a fraction by negative 1? Well, it turns out there's 3 good choices. I'll show you all 3 of them. The first one is to simply take that negative 1 and put it in front of the fraction. Nothing wrong with that. The second option is to multiply the fraction by negative 1 over 1, effectively multiplying the top by negative 1. And the third option is to multiply the bottom by negative 1. Now, one thing you may be asking yourself right now is, why are there options? Isn't there just a single way to multiply by negative 1, and why would I want to have options? Well, it turns out these 3 different options are good in different situations, depending on which one sort of cleans up or makes the answer look neater. And sometimes you'll find option 1 works, or 2 or 3 makes a neater answer. Now they're all mathematically correct, but let's look what happens to the algebra symbols under each choice. Before I do that, take a moment to notice that all of the 3 things in these boxes all represent multiplication by -1. Even in option 1, simply putting a negative in front of the fraction indicates a multiplication by -1. So while they're all correct, let's see which one gives us a nicer looking answer. Option 1 is about as simple as it can get. In option 2, I'll distribute the -1 through the numerator. But notice the numerator now is simplifiable. You'll notice algebraically those 2 things are the same. And in option 3, if I distribute the -1 to the denominator, I get this, and that's about as far as I can go. Now the question, of course, isn't which one is right. They're all right. The question is, which one gives a nicer looking answer? Now, many math students will look at these 3 things and say, I don't have an artistic opinion over which one looks nicer. I just want credit on an exam. Okay, fair enough. Chances are your teacher, professor will allow any of these answers. Personally, I think option 2 is the nicest looking, simply because it involves the least number of symbols, particularly the least number of negative signs. So I'm artistically disposed to like option 2 better. That doesn't mean it's the only way to express the answer. But let's recall, math is as much of an art as it is a science, and so I like option 2, and I'll leave my answer that way. Now you've seen a lot here, so let me summarize. You're going to be given a polynomial divided by a polynomial and told to simplify or reduce. You're going to factor, and one of 2 things will happen. Maybe none of the factors match. If that's the case, your polynomial fraction, your rational expression, is not reducible. But if 2 of the factors do match, you will split that fraction into a product of fractions, pulling the like factors together, then asserting that anything divided by itself is 1, and then asserting that anything times 1 is itself. That's the general strategy. Now sometimes you have to use the -1 rule for opposite subtractions, and sometimes you have to do this more than once, but that's the general roadmap of how to reduce a rational expression. And that completes the second of an 8-video series on rational expressions.